Hi, good morning. This is going to be a series of lectures on infinite series. Those of you who had been watching my videos on analysis will know that I have covered almost all topics from our book on real analysis written by Ajit Kumar and Kumaresan, titled A Basic Course in Real Analysis, except one topic, namely the infinite series. Of course, I believe I had I released two or three videos on infinite series. Okay, one is on Merton's theorem on Cauchy product, another one is Abel's limit theorem for power series. But those who watch may also know I made efforts to recall whatever is the base necessary requirement for that particular theorem. Okay, but here we are going to start from the beginning, and a very systematic way we develop everything. Okay, and yeah, one more thing, if you look at a lot of textbooks of Indian origin, you will see there will be about two dozen tests of convergence, and there will be a lot of circus. Okay, to use this test or that, use that test, nothing is clear, you just keep doing. But remember, from the point of view analysis, the most important thing is you should understand the concepts basis very well, and you should know some of the most important and very useful tests. Okay, for your life, that's more than enough. Okay, I am sort of working analyst. Okay, I never needed anything more than what I'm going to talk about. Okay, so do not worry about, okay, that test, this test is not found in my lectures. Don't worry about that. Okay, let's get started. Yeah, so this is the title, infinite series. Okay, it's started on Lohiri, and it's a Bohi for Tamil people, and the reference is Ajit Kumar and Kumaresan, a basic course in real analysis. Please buy it. Indian reprint is available. Do not buy US edition, that will be very expensive. And this is the URL. Okay, the link for my YouTube channel. And as I have been saying, the YouTube, the way it arranges the videos are essentially chronological, and it's very difficult to find in a given topic. Suppose you want to learn a given topic, what are the videos and in what order you have to learn or watch those videos is never clear. Okay, so what I did was I have prepared a list of videos. Okay, and you can download it from the site. Okay, that, so each topic wise, let's say infinite series, then it will start with infinite series 1 2 3 4, like that, continuity 1 2 3 4, like that, so that you know which order you have to watch them. Okay, I hope you enjoy. Do that. Let's get started. Okay, let's quickly recall in basic thing. If I have something like n numbers, a1 a2 an, real numbers, okay, then I can add them sequentially, a1 plus a2 plus a3 plus an. Yeah, but remember, R is a field, therefore there is additive addition is commutative as well as associative. I do not know how conversant you are with the basic arithmetic, because nowadays, you are all young generation with the calculators, etc. Okay, whenever we do, we try to group. If you look at some Kirana shop fellows, very old people, you will see he will quickly add much faster than I could or you could do. So, for example, if you have to do something like that, okay, he will quickly say this is 20 plus 20 40 40 plus 50. He will not add sequentially 12 plus 14, after that 7, after that 3, after that 6, after that 8. He may not add it. Okay, this is 20 plus 20. Okay, and that's it. He will quickly add, right? So sometimes he may even group terms. For example, suppose I have something like 12 plus 7 minus 8 plus 6 plus 3, okay, minus 10. Okay, then you can add 12 plus 7 19, 19 plus 6 25, plus 3 28, minus 8 20, minus 10. Okay, 10. So again that you know the answer. That is, I add these things. Or are you following? Yeah, right. Okay, so you can just group the terms. For example, I can add these two things. Okay, 12 plus 1 13, 13 plus 9 22, 22 minus 10. Oh, 22. I hope I'm doing, yeah, this is 12, this is minus 1, therefore 11, 11 plus 9 20, 20 minus 10 10. Okay, the answer. Okay, correct. So you can also group terms. Okay, for example, I can group these two terms. 7 plus 3 is 10, minus 10, therefore this is out. Okay, I hope I'm doing it correctly. I'm always worried. Okay, now 12 plus 6 is 18, 18 minus 8 is 10. Okay, so we do lot of such things. We use our commutativity or associativity, right? Okay, now analysis an infinite process. So I may be given for each natural number n, I may be given a real number an. That is same as saying I am given a sequence an. Now I want to add them, but remember, when I want to add, okay, it goes on. I cannot keep writing all these things. Okay, and this is just a shorthand notation. You use this. Sometimes people will write n to infinity, but usually I will write it only summation an over n. Okay, that means n in natural numbers, unless I say n equal to 1 to some 10, like that. Okay, if it is something like a1 to a20, I may write it as n equal to 1 to 20. If I don't write it, it is all. Okay, that's my way of writing. Because I used try to avoid writing n equal to 1 to infinity kind of thing. Okay, right. Now what is meant is we have to sequentially add. So in the beginning, okay, few hundred years ago, okay, were mathematicians, okay, they tried to do whatever they did with finite sums. That is, they tried to group terms, okay, and change the order, and so that the addition summing becomes easier, so that you get the result. That's whatever you see, that just now I showed. Okay, there are many ways of adding. Whichever is convenient to you, just add, so that you get easier answer, right? You don't add sequentially. You don't add a2 to a1, and to this sum you add 3, to this sum you add a4. You don't do that. Okay, so what they did, let us look at the simplest case. Suppose this is my an, this is minus 1 to the power n minus 1. Therefore the series I will write it like this, and so on, right? So suppose the sum is yes. Okay, I add it, so I get a sum yes. Okay, notice that this is the, I am just trying to say about few hundred years ago how they did. Okay, then what they did is they tried to group. One guy grouped like this. Okay, this is a grouping he did. So he said it is going to be 0 plus 0 plus 0, etc. Therefore he thought s must be 0. Okay, there was another guy who did like something else. What he did was he grouped only this. Therefore for him it same term will be 1 plus 0 plus 0 plus 0. So he thought the sum must be 1. Okay, now they are confused. Which is correct? You cannot get two answers. Do you follow that? So they were a little worried. What is happening? Okay, why it happened? Remember, it happened because here you grouped the terms like this. Okay, whereas here you group terms like this. There may be more complicated ways also I can do, but I just want to look at the simplest case where this already gives a problem. Okay, so they wanted to know how to define how to define the sum of an infinite series, so that you don't get different answers. All of us will get the same answer, except that is we fix the notion. This is how I will do that. This is what I mean by sum of an infinite series. I'm saying all these things because students are not given, they just start with something. Okay, lot of tests and you keep on computing, but the concepts are never understood. Okay, that's why I'm spending much time. I hope you all understand this, right? Okay, so remember, so what I said is the idea is to add sequentially. So I add A1, so I call it S1, and add A2 to A1, I get S2, and add A3 to S1, so this is nothing other than S1 plus A2. This is S2 plus A3. Therefore, I add Sn, that is like sequentially adding. Remember that? This is the word you have to use. S1 plus n minus 1. You see that I am using this here. This is nothing other than Sn minus 1 plus an. You understand that? Now, so you are given, started with this sequence of real numbers. You got, what is this? Just a notation. Okay, this has no meaning. Okay, then for this I call it infinite series associated with the sequence an. Okay, the infinite series is different from the sequence, right? Then what we get is, we get another sequence, Sn. How do I define Sn? So this being a finite sum, I don't care how you add. You can add whichever way you want, whichever way you convenient, because Sn is well defined. Whatever way you group, whatever order you change, it does not matter. Okay, you get the sum. So I get this sequence. So now again, intuitively, what did I say? My infinite series is sequential adding. You keep on doing. That means I get Sn here, then I get Sn plus 1 here, and so on. Therefore, okay, this is a typical of mathematics. You reduce the problem to an earlier problem which was already solved. So I am going to say the sum of the infinite series summation n is the limit of this. Okay, these Sns are called partial sums or nth partial sum. Okay, so I have a meeting. I'll take a break and come back. Hi, the meeting is over. Let me resume wherever I left. So let us quickly recall. I am given a sequence an in R. Okay, then this is a symbol. Okay, this is what I call this is infinite series. I say this is the infinite series associated to the sequence an. Okay, this is just a formal symbol, formal, and it's very symbolic. Okay, it's a just formal symbol. We are going to attach a meaning to this. So what we do is, the first thing is, intuitively we want to add a1 plus a2 plus an, keep on doing that in a very sequential manner. Therefore that allows me to look at what I call Sn, which is a1 plus a2 plus an. These are called the nth partial sum. Of the series. Okay, right. Okay, and notice that when I want to add a1 to an, this is a finite sum, so I can do any kind of grouping, reorder them, okay, and use commutativity, associativity, everything. So it does not matter. Sn is always well defined. Okay, this is the advantage. Now what do? I want to say, if Sn, suppose this is a sequence, again a sequence in R, right? And this is a finite sum, therefore Sn is a real number. Okay, this is a sequence in R. Suppose Sn converges to S, a real number. Okay, so we are assuming, it may not assume Sn converges to a real number S in R. Okay, then intuitively I think I summed up, okay, the infinite series an, that is a1 plus a2 plus an dot dot dot, okay, sequential manner, okay, in an orderly fashion, a1 plus a2, a1 plus a2 plus a3, and kept on adding. Okay, in the limit I get something else, so I want to declare it is a sum. Okay, then I call S as the sum of the infinite series. So we denote it by Okay, these are all okay. Now remember, the first thing is, whenever you write this equation Sn equal to S, okay, this is the, what does this stand for? That is what you should emphasize. It's not ordinary finite sum or anything. Okay, the sum of this infinite series is limit of the sequence of partial sums. Therefore, okay, I am going to tell you the trade secret. Okay, whenever I deal with infinite series and their sum, okay, I think of this infinite series not as this symbol but as a sequence Sn of partial sums. Okay, this is okay, this is like anything to do the infinite series. Okay, any analysis I want to do, okay, the other for its existence is the sequence of partial sums. Okay, so when you give me something infinite series, I always think of the partial sums. That is the crux of the matter. Therefore, a modern way of looking at an infinite series, suppose I am given a sequence an of real numbers. Okay, this infinite series actually stands for Sn. Okay, this is a symbol. This symbol denotes only the sequence of partial sums for me. Okay, this is a way of, okay, different way of thinking. A perspective changes. This is not usually taught the way in usually textbooks or by teachers. Okay, I am just telling you how I think of it. Okay, the summation an, the infinite series an, is just a symbol for me. What does it stand for? It stands for sequence of partial sums Sn. What is Sn? That is, you add a1 plus a2 plus an in a sequential fashion. Okay, that's it. Have you understood? Okay, say pause, review, proceed. Okay, and therefore this equal to, yes, this, what is this, is a symbol again. What does it stand for? It stands for limit of the sequence of partial sums. Yes, that's it. Okay, this is a shorthand notation for this morning. Try to change this perspective. You will see, once you understand this way, all the conceptual things, theoretical results will become crystal clear to you. Okay, whereas you will be looking at a1 plus a2 an, although you are doing with a finite sum, which is very, very harmful. Okay, and it will lead you to mistakes. Okay, let's look at some examples. Now let's look at the example where an is minus 1 to the power n. Therefore I want to look at an. So what is this an? I have to look at what is s1. s1 is 1, s2 is 1 minus 1 0, s3 is 1 minus 1 plus 1 1, and s4 is 1 minus 1 plus 1 minus 1 0, and so on. Therefore what do I have? I have s2n minus 1 equal to 1 and s2n equal to 0, right? Therefore the sequence Sn is 1 0 1 0, etc. Okay, do you understand? Right. Therefore, okay, does the series have a sum? Yeah. Does the series an, does it have a sum? That is, can I sum it? No. If I can sum it, what does it mean? The limit Sn should exist. That means Sn must be convergent, and its limit is what I call as. But this, as you know, 1 0 1 0 is not convergent sequence. Therefore I say the series does not have a sum. Do you understand? So let us make a definition. Let an be a sequence in R. Let, this is just a notation again, be the associated series. We let Sn equal to a1 to an. Okay, then I am making two definitions. We say that the series is convergent. Remember, if I don't write, this means yeah, okay, a for all n in natural numbers is convergent. If the sequence, but for me, what does the infinite series stand for? It's a sequence of partial sum. Therefore, convergence of the infinite series, what should it mean for me? If the sequence Sn of partial sums is convergent. Okay, and 2, if this is convergent, then we denote this by an equal to this equal to s, where s is the limit of Sn. When this is convergent, it means same as saying that is Sn is convergent. Alright, and therefore let S be the limit. Then we say we call S as the sum of the series. Notice that the sum is not simply like a finite sum. What do you do? Sns are finite sums, and that's a sequence. Look at the limit. If the limit is S, that is what I call as a sum. Okay, so just because the sum, don't think of is your primary school sum. Okay, that's a finite sum. This is not the sum. Okay, this is just a notation. Okay, we just call it a sum. Okay, so let us go back to the series an, which is given by this. Therefore, what do I know about this series? This is not convergent. Why? My Sns are this sequence. Okay, so sorry, the sequence Sn is this. So this is not convergent. Therefore, I say the series is summation an is not convergent. Okay, and remember, if you have followed my lectures on sequence, whenever a sequence is not convergent, I call it divergent. Okay, divergent for me is same as not convergent. In the modern mathematics, that's how we usually understand. So we also say it is divergent. Don't think of it divergent to infinity, etc. Nothing. It simply means when I say it's divergent, it is not convergent. Okay, are you following? Right. Now let's look at the simplest example. Now let me say an, okay, a sequence, constant sequence C for every n. Okay, now let's look at the infinite series n. Now I want to know whether it is convergent or not. If it is convergent, what is the sum? Is the question clear? Right. So let us look at it. So what is my S1? C. What is S2? C plus C, which is 2C. Therefore, what is Sn? N times C. Right? Okay. Now, when is the series is convergent? If only if the series Sn, that is, the series is convergent. Right? Now this is the sequence Sn is convergent. But the sequence Sn is, the nth term is Nc. Now the moment you see Nc, you should always remember what should you recall from real analysis? Archimedean property. Right? If it is a convergent thing, so sorry, Archimedean can come later. If it is convergent, then it should be bounded. You understand? So if suppose the Sn is convergent, that if and only if, no, not if and only if, it means the sequence Nc is bounded. What does that mean? That means for all n in n, my Nc, okay, modulus should be less than or equal to m. There exists m positive, so that this happens. That means my mod C is less than or equal to m by n for all n. Okay, therefore by Archimedean property, mod c must be 0, because if mod c is not equal to 0, then n times mod c will, there exists n, so the n times mod c will be greater than m. You understand? Therefore n mod c must be 0. That means c must be 0. Do you understand that? So what did we conclude? If an equal to c, and if you say the series an is convergent, okay, this implies c must be 0. It's a necessary condition. Because I assume the series is convergent, then I arrived at c must be 0. Right? Okay. Now, is it sufficient? Suppose c equal to 0. Then what is Sn? Sn is 0 plus 0 n times. Therefore, it is 0. Therefore, Sn is the constant sequence 0. Right? Therefore, what is the limit? Sn. That is 0. Therefore, this series is convergent and the sum is 0. Do you understand this? Now, using our definition, we rigorously proved summation of an, where each an is 0, and summation of c, if c is not 0, then it is not convergent at all. Have you understood that? Yeah? Pause, review, proceed. Okay. Notice that I had asked some PhD interview and postdoc interviews this question: summation an equal to what, where an's are 0. There are candidates who said it's infinite times 0, it's indeterminate, and he said by induction summation an is 0. So by induction Sn is 0. But why this infinite series is 0? That is because each Sn is 0, and then I have to look at the limit of the sequence of partial sums. Remember, as I said, okay, this is a golden principle. Keep this in mind. What is the golden principle to deal with infinite series? Whenever you see the infinite series an, okay, think of it as a symbol for the sequence Sn of partial sums. Okay. So this is the basic thing, right? Okay. Before I stop the lecture, let us look at the most important example. Okay. I fix a real number r between 0 and 1. When r equal to 0, what I am going to do is already then. Let me define an to be r power n. Okay. Those who have watched my videos on sequences will know r power n goes to 0. Yeah, you know that. Anyway, let's go. Right now, I want to know whether this series is convergent. If you want, simply say r is positive. Okay, let me not even look at it. Let me look at r is positive. Right, then I want to know that this is convergent. Right, so what should I do? Now all of you know what is the trick. We should always look at the partial sum. What is the partial sum? So to make life easy here, usually one assumes that is n is in z plus, that is n union 0, so that a to the power, see, a 0 will be r to the power 0 will be 1, so that will be taken care. Therefore this will be, for any natural number n, in n, this will be 1 plus r to the power n. This you know from your high school, it is 1 by r to the power by 1 minus r if r is not equal to 1. If r equal to 1, you know it is n plus 1. Right? If r equal to 1, Sn is n plus 1. And this sequence Sn, in this case, this is not bounded. And hence, this series 1, the constant series 1, this is not convergent. This we already know. Because when r equal to 1, it becomes a constant, the series of constant terms, and we know it is not convergent. We had already seen it. Yeah, I'm just giving a proof. So let me assume r is not equal to 1. Let me concentrate. So my Sn is going to be 1 minus n to the power r plus 1 by 1 minus r. Right? Now I want to know that this is convergent. Okay? Now, suppose, again let us use, okay? Yeah. So this is, remember r is fixed, therefore it's 1 minus r minus, okay, 1 minus r to the power n plus 1. Right? So this is 1 by 1 minus r minus 1 by 1 minus r into r to the power n plus 1. Remember, this is like a constant. R is fixed. Do you remember that? R is fixed. There is no n. Okay, therefore this is a constant. So the convergence of Sn, I am writing Sn as something like an minus bn. Right? Now ans are constant, namely 1 by 1 minus r. And bn's are a constant 1 minus r times r to the power n plus 1. You understand that? So I know this series is convergent. Right? Therefore my Sn minus an is your minus bn. Right? This is, notice that this is a constant sequence, namely 1 minus r, 1 by 1 minus r. Right? So this is convergent if and only if bn is convergent. Do you understand that? Therefore Sn is convergent if and only if the sequence minus bn are the same as the sequence bn is convergent. Yeah? But what is the sequence bn? It is 1 by 1 minus r to the power r to the power n plus 1. And this is a constant. Therefore bn is convergent if and only if r to the power n plus 1 is convergent. Right? This you already know. Okay, from my lectures on sequences, convergence of sequences, or even otherwise from your earlier experience, you know that if r is greater than or equal to 0, r to the power n is convergent if and only if 0 less than or equal to or less than 1 or equal to 1. Is that clear? Yeah? Right. Now remember, we are assuming my r is not equal to 1, therefore I can as well assume this is convergent. This is a correct statement. Okay, but remember my r is not equal to 1, therefore this is convergent simply means if and only if 0 less than or equal to or less than 1. Are you convinced? Please pay attention. When r equal to 1, that case I already taken care of. Therefore I am assuming r is positive but r is not equal to 1. Therefore my Sn is convergent if only bn is convergent, but bn is 1 minus r. This is a constant time r to the power n plus 1. Therefore this is convergent if only if 0 less than or less than 1, because r is equal to 1 is ruled out. Therefore r must be between 0 and 1. Do you follow that? Very good. Then if that be the case, what is the sum? Therefore let us first write down summation an, that is we will write it as r to the power n. Now I will write it n is greater than or equal to 0. Okay, is convergent if and only if 0 less than or equal to or less than 1. Okay, once it's convergent, then I want to know what is its sum. So what is the sum? Sum, yes, is nothing other than limit of the sequence of partial sums. But what is this? This is a limit as 1 by 1 minus r into 1 minus r to the power n plus 1. Right? So now remember my 0 less than or less than 1, therefore r to the power n plus 1 goes to 0. Right? Therefore this goes to 1 by 1 minus r. Right? Therefore what I have shown, so let us fix 0 less than or less than 1, then define an to be r to the power n, then this is convergent and this is equal to 1 by 1 minus r. And remember, I am starting with n equal to 0 onwards, and the sum of this infinite series is 1 by 1 minus r. This is called the geometric series. Okay, and then if r is greater than or equal to 1 and an equal to r to the power n, then okay, is not convergent. Okay, because we know that r to the power n, if r is greater than or equal to, or if r is greater than 1, okay, this is unbounded. Okay, but on the other hand, r equal to 1, the sequence Sn, okay, is n, and this is unbounded. Why does Rn equal to unbounded mean? Gives me, are you following me? Suppose r is greater than 1, then the sequence r to the power n is unbounded. Why does this imply Sn is unbounded? Remember, my Sn is 1 plus r power n, therefore greater than or equal to r power n. You understand? Right? Therefore, if Sn is bounded, remember my Sns are all greater than or equal to 0. Actually greater than or equal to 1, because I am assuming r is greater than 1. Therefore, it is simply saying it's bounded above. Right? Therefore, let's assume Sn is less than or equal to m. That would mean Rn is less than or equal to m for all n. But I know Rn is not bounded above. Why Rn is not bounded above? Let me quickly recall the proof. Do you remember? This is the trick I always do. Whenever I use some fact, I try to see whether I can quickly go through the proof. When you write r equal to 1 plus h, where h is positive, if r is greater than 1, then r to the power n by binomial expansion will be greater than n times h. Right? This is binomial expansion, or somebody's inequality, Bernoulli inequality. Okay, many people may not remember Bernoulli, but binomial you can write it because h is positive. Okay, this is going to be 1 plus nh plus n choose to h to the power n minus 1 and so on. H squared and so on. Okay, these are all positive terms. Therefore, this is greater than nh. Right? By Archimedean property, h is positive. Therefore, by Archimedean property, nh is unbounded. Okay. So remember that I have gone through all the proofs quickly. Okay, this is the proof which happened in the first 10 lectures of real analysis, but we are quickly recalling the proof. Okay, let's go back. So please go through. You will see this geometric series is a fulcrum in the study of infinite series. Okay, I'll come to that later more, but go through the proof quickly. Okay, the geometric series are summation r to the power n running from 0. Right? Okay, and this is convergent if only if for r non-negative, 0 less than or equal to or strictly less than 1. If r is greater than 1, it's not convergent. Greater than or equal to 1, it's not convergent. Okay, and we are assuming r is non-negative here. What happens when r is negative? That we'll look at in the next lecture. Please go through, but at the end of the lecture you should remember my series summation an n okay over n is a symbol for me for the sequence Sn of partial sums. Okay, remember that. That is the mantra to work with infinite series. Okay, we will meet again.